Hey guys, so I realize in the homework you have a problem that looks really similar to the ones we went over in the lecture, but it's actually a special case. It's kind of different. So I wanted to give you one more example of how to go over these. So again, if we look at this at first, it looks just like everything else we've done. So the first step is we would need to pick a ground, and so I'm going to put that right here. And just like before, we would need to label all the nodes where we don't know the voltage. So since I enabled this ground, I know this is 0 volts, and it means everywhere along the bottom is 0 volts. I know that there's a 10 volt increase from here to here, so if it goes up by 10 to get to here, then this must be at 10 volts. Now I'm looking at this spot, and at first you might think, well, that's 5 volts, right? Because there's a 5 volt supply right here. But it's actually not. That's not how voltage supplies work. Remember, what this power supply means is that this spot here is 5 volts greater than this spot over here. The problem that we have is we don't know what that voltage is. And so since I don't know what this is, I don't know what this is either. I know it's 5 volts greater than the one on the right, but I don't know what that is. And so we actually don't know either of these voltages. And the reason is that because this here is not ground. The only way that we knew that it was 10 over here is because 10 is greater than 0, because we knew it was ground. And so what that means is this is our VA, and this is our VB. And again, we know it's 0 at the bottom, 10 in the upper left, and those two spots. So let's try to solve it now. And this isn't going to work, but at first I'm going to try to solve it the way we've always solved these problems. So I'm going to start at this node, and we'll work with the current going this way. That's VA minus 10 over 2. Then we'll do the one going down. That's VA minus 0 over 8. And then we'll do the current going this way, and this is where we run into a problem. I can't write an equation for the current going that way. Remember, that's a power supply. Its whole purpose is to inject, induce, whatever you want to say, but cause current to flow. And so because of that, I can't write an equation for that. And so the way that we've been solving this so far isn't going to work. There is a way to solve it, though. Remember what we talked about Kirchhoff's current law. That's how all of this works. What we're going to every node, adding up the currents, and setting it out to 0. So far, we've looked at very tiny nodes, right? One intersection, just like this, and we add up all the ways the current leaves. Remember, though, that Kirchhoff's current law doesn't just work at one spot. We can make the node as big as we want, and it will still work. And so that's exactly what we're going to do. What we're going to do is we're going to create something called a supernode. Like Superman? Supernode. And so what I'm going to do is instead of just looking at VA, I'm going to draw a circle on my actual diagram. It doesn't have to be a circle, it could be any shape. And I'm going to say instead of just making that one little spot a node, I'm going to make this whole thing one giant big node. And so notice my goal here is to make sure I get the entire power supply within inside of that node. Now remember, Kirchhoff's current law still has to work. So if I end up the current going this way, this way, this way, and this way. Notice that what I've essentially done is I've drew anywhere that that circle has current leaving. We can see that because it crosses the line. I'm going to add up all those currents that are leaving. And so this will actually still work because Kirchhoff's current law works at one spot or as big a spot as we want. And so I'll start with this one right here. Again, we still have VA minus 10 over 2. Plus, we'll do the one going down now. That's VA minus 0 over 8. I'm going to do the current going this way. And now we still know the current here, right? It's still VB minus 0 over 6. And then finally, I'm going to do the current up here. And that's VB minus, it's 10 on this side, so VB minus 10 over 4. And so notice everything, once we've created that big node, it all works out exactly the same as we did for all the other problems. So now we just need to simplify this and put it in standard form. And so what divides all of these evenly? Looks like 24 does. Again, if you didn't see that, you could multiply them all together. You'll just be dealing with bigger numbers. But 24 is going to divide evenly amongst all these. So I've got 24 VA minus 10 over 2 plus 24 VA over 8 plus 24 VB over 6 plus 24 VB minus 10 over 4 equals 0. Alright, so now we just need to multiply it out. 24 divided by 2 is 12. So that's going to give me 12 VA minus 120 plus 24 divided by 8 is 3. So plus 3 VA. 24 divided by 6 is 4. So plus 4 VB plus 24 divided by 4 is 6. So plus 6 VB minus 60 equals 0. Now we got to group all of our VAs and VBs together. So I've got 12 VA plus 3 VA. It's going to give me 15 VA. Now we'll get all the Bs. 4 VB plus 6 VB plus 10 VB equals. Now we need to move our constants to the other side. So I've got negative 160 plus negative 60 gives me negative 180. So I move it to the other side and I get 180. So we've got our first equation. But now we have a problem. Notice that I can't solve this yet. I have two unknowns. I have both VA and I have VB, but I only have one equation. We're going to need two equations if we have two unknowns. So the issue is if we look back up here, there aren't any other nodes, right? We've basically taken all of our nodes that we don't know the voltage for, so we can't write our normal equation. But remember, whenever we're doing this, I said treat it like a puzzle. We just have to find any other equation that we know to be true. And so, can you figure this out? Can you think of what else we might use as an equation? I can't wait till we're back in class together and I can actually hear you. I'll give you a hint. It happens around here. Well, I don't know what the voltages are there, but I do know that whatever VB is, if you add 5 to it, you get VA. Right? Because that's what this power supply tells us. It says that if you take VB and you go up by 5, you're at VA. And so I can use this as my second equation. It's that simple. And pretty much every time you use a supernode to enwrap one of these supplies, you're going to be able to do that. So let's go down here and write that. So I said I had VB plus 5 equals VA. Just like before, we still want to put it in standard form. So I'm going to bring the VB over to here. And that's going to be VA minus VB equals 5. And now I have my two equations. So again, we're going to do elimination. What I'm going to do is I'm going to take this one, just like it is. 15 VA plus 10 VB equals 180. And I'm going to take this one and I'm going to multiply it by 5. Not by 5, I'm going to multiply it by 10. That way the VBs cancel out over here. And so that's going to give me 10 VA minus 10 VB is equal to 50. And so you'll see that right here, these two cancel out, and that's going to give me 25 VA is equal to 230. And therefore, VA is equal to 230 divided by 25, which is, calculator please, 230 divided by 25. 230 divided by 25, that's it, right? 9.2. So now I've got our first voltage. We know what VA is. Now all we have to do is plug that back into our equation. So I want to solve for VB. So I'm going to rearrange this. I'm going to say that I'm going to move VB over here and the 5 over here so it becomes positive. So that's going to be VB is equal to VA minus 5. And that should still make sense. Remember that whatever VA was, 5 less than that was VB. And so now if we just plug in our value for VA, we get VB is equal to 9.2 minus 5. And so VB must equal 4.2. And that's it. That's how you can solve this one. So now you can tell everybody you know what a supernode is. I hope this helped. Talk to you guys again soon.